University of Southampton that we'll be talking about building a bridge between anti-de Sitter and details.
Thank you, Joaquin. So I changed the title so that it's clearer for the start of what I will be trying to do in the next hour. But first I would like to thank Joaquin and Andrea for this very nice workshop and for inviting me to this seminar. And of course I would like to thank everybody for staying until the last talk. In exchange I will try to I have a lot of things to say. I will try to spend my 50 minutes or so, and for this I will rely on the workshop of the white rabbit here. And hope for the best. Anyways, general relativity now is 100 years old, and we got a lot of deep insights on it, on the working of gravitational forces, and of course, while, for example, we predicted the existence of black holes, and last year we had this beautiful detection of black hole mergers with the gravitational wave detectors. Okay? That being said, there are many things that we still don't understand, and in particular, it's still not clear how to reconcile general relativity with quantum mechanics. In the last century, essentially people have been concentrating on asymptotically flat solution of the Einstein equations. Okay, and we have learned a lot, and so we know how to define an S matrix on asymptotically flat spacetimes, so in and out states. This allows us to define quantum field theories on curved background and do some kind of quantum gravity. And this allowed the discovery of Hawking radiation, black hole dynamics, and so on. And more recently, there have been new, interesting attempts at using the BMS group to understand, for example, the Schwarzschild, the microstates of the Schwarzschild black hole. And then there are plenty of other interesting results. In particular, we know a lot of solution generating techniques in asymptotically flat spacetimes. And of course, we know how to quantize the strain on cosmic spacetime. Okay. In the last 20 years, however, people have been focusing mostly on anti-de Sitter gravity. And the reason is that asymptotically, the asymptotic symmetry group of anti-de Sitter is the conformal group in one dimension less, and this, as Dario explained to us yesterday, is linked to the fact that we can describe anti-de Sitter gravity is due to some field theory in one dimension less. And in particular, the best understood example of this is the correspondence. And this gives us very powerful tools and deep insights again on how gravity works, in that gravity is holographic on these spacetimes, okay? And therefore we can describe all the dynamics in terms of a field theory in one dimension less. Actually, in some sense, we can say that the Supermanian-Mills theory in 4 dimensions gives us a complete non-perturbative definition of quantum gravity. So actually, quantum gravity is a solved problem, right? And of course, it's difficult to rid of what we want from it. And then there are so many results on the sector. I cannot go through all of them, but for example, why the Schwarzschild black hole is maybe the hardest to understand. In anti-de-Sitter we have a good understanding of what a Schwarzschild AES black hole is. In particular, when they are large, they are cosmologically large, these black holes, they can be described in terms of some fluid gravity correspondence. So we can describe them in terms of some fluid dynamic theory. Now, the thing that is interesting here is that these two diagrams that I showed look a bit complementary, because the things that we understand quite well on one side are the ones that are understood, are less understood on the other side, right? For example, we have quantum gravity on anti-de-Sitter space, and we understand well how holography works, but on the other hand, even though all the arguments for holography are independent of the presence of cosmological constants, that they depend on entropic arguments on black holes and numbers of degrees of freedom. For asymptotically flat spacetimes, we don't know how to formulate holography. So it would be really great to have some kind of bridge between these two worlds, which could allow us to take concepts and tools from one side and transfer them to the other in both ways. And what I want to show you today is that we are starting to uncover such a bridge. It's not yet that solid, but we believe it will teach us a lot, in particular about holography in vacuum Einstein gravity. Some references. The original bridge, this is what we call the anti-de-Sitter rich flat correspondence, was developed with John Hansen, and Costas Kenderis in these two papers. And I will spend most of the time discussing these things, because I think it's important that to convince you that how this works and how useful it can be. But then I want to show you also some recent results where Costas Kenderis were generalized and show that this bridge can be extended, and it's not just the result of some very peculiar symmetries that we have. This is a paper that should come out very soon, but this is also a statement that has been true for a very long time. But we have smoothed out all the rough edges now, and the draft is in the good state, so I believe it will not be very good. Okay, please interrupt me at any time if you have questions. Okay, I will start with a short introduction of some concepts of holography that we will need, and then we will see how far we can go. Okay? So, if there is no question, I will start with a lightning review on holography in anti-de-Sitter spacetime. Well, already from yesterday, Dario explained us how the string is called. Okay. Any gravitational theory is expected to be holographic, and it should have a description in terms of a non-gravitational theory in one dimension less. And as Dario showed us yesterday, the best understood holographic dualities are the top-down ones, because they come from string theories on some limits of grains. And for example, the most well-known example is the ES-CFT duality and ES5 process 5 and this theory. in 4 dimensions. Now, all these all these conformal field theories actually contain a universal sector that describes all the correlators between the stress tensor. The stress tensor is always an operator that is there, and this universal sector, from the point of view of ADS-CFT correspondence, is really described by pure ADS gravity, that is Einstein-Hilbert term and a negative cosmological constant. So, during all my talk, I will always consider pure gravity only, with or without cosmological constant. I will not talk about extra matter or so. Now, the thing is, how can we extract from the gravitational theory correlators of the CFT? And this works like this, for example. I guess I cannot do anything, right?
No, I think.
Okay. So, well, let's start from the vacuum, and the vacuum of the CFT is represented by the ADS solution, and this is ADS in Poincaré coordinates, and as you well know, there is a conformal boundary at r equals 0. Here r is the holographic coordinate, the one orthogonal to the boundary, and we have the Minkowski metric here, that is this conformal metric boundary. Now, when we want to solve the Einstein equations, with ADS boundary conditions, well, we have to impose some boundary conditions in a consistent way. And in the case of ADS, what you do is that you choose a conformal field class for the boundary metric. That is, you give the metric of the boundary up to some local conformal factor. Now, what Pfefferman and Graham showed a long time ago is that once you choose your conformal class, then you can integrate order by order in a perturbative series in the holographic coordinate your Einstein equations, and you obtain what we call the Pfefferman-Graham expansion near the boundary. Okay, and the peculiar thing here is that in this expansion in the radius, in the holographic direction, the first term is free. It's the boundary metric that we chose for our problem. But then all these blue terms are completely fixed up to order r to the d. And they're completely determined algebraically in terms of this G0. Okay. However, once you arrive to this order d term, you discover that this tensor here is not completely fixed. It is traceless and conserved, but otherwise it's. So you have to say who this guy is also. And from the point of view of the CFT, well, this boundary metric is simply the source for the stress energy tensor of the CFT, while GD is proportional to the expectation value of the dual stress energy tensor. So, if you want to calculate observables of the CFT, this is correlators between this stress energy tensor operator. What you do is simply you take your metric, you perturb it, and then you solve the Einstein equations perturbatively in H, but but the solution has to be exact all the way in the bar. Okay, so you cannot just work usually in this Pfefferman-Graham coordinates because they will have some finite rates of convergence. And if you do this, then you expand in this Pfefferman-Graham expansion, and what you obtain is you can read off order by order in this perturbation the various correlators. So The simplest one you can think is the correlator between two stress tensors, well, all you need to do is to find a linear perturbation around Poincare, the Poincare metric, that is regular everywhere. Okay? And this fixes the perturbation to be of this kind, and you get this cell function here. And if you expand in the orographic coordinates this function here, you see, well, this one means that this is your boundary metric, and then r to the b here, the coefficient of r to the b gives you the stress tensor. Sorry, it's the part proportional to h, which gives you the two-point function of the stress energy tensor. Okay, and this is precisely the stress energy tensor for a conformal field theory in an odd number of dimensions. Okay, so this is how you calculate correlators in ADS-CFT, and well, we will want to see what happens to these correlators when we transfer them to Minkowski space. Now, the question is, can we just do the same thing for asymptotically flat spacetimes? And this has been tried by many people, but it's very difficult and not clear how to do it, because there are essentially two obstacles to do a similar analysis for asymptotically flat spacetimes. First of all, the fields that parameterize the boundary conditions are constrained, so there is no boundary metric that is completely free that you can choose as usually boundary condition. You get some differential constraints on top of it. And also, well, you get infinities in the official action, and these are non-local in this field, so it makes all the holographic program very hard to be transferred as it is to asymptotically flat or vacuumized gravity. We will see that actually we will be able to encode this holographic data in a different way. Is there a question? Okay, so let's get into the main topic, and let's see what is this ADS rich flat correspondence. Okay, actually it's a simple mathematical map that allows you to take families of asymptotically ADS metrics and map them to rich flat metrics. Okay? And its origin can be easily seen from sorry. It's really not really good. I'm sorry about that. Okay, it can be easily seen by performing dimensional reductions of the Einstein-Hilbert action for ADS or just Minkowski. Okay, so for example, let's start with ADS gravity, and in d+1 dimension, and let's suppose that there is some torus over which we can perform a Caruso-Klein reduction. Okay? We will do just a dimensional reduction, a diagonal dimensional reduction, which is consistent using this ansatz here, okay, which is just a diagonal ansatz. And as you can easily imagine, all you obtain is a theory in the remaining p+2 dimensions that has, well, a graviton and then also a dilaton phi. Okay? And this the coupling constants that appear, alpha and beta, well, they're related, they depend essentially on the dimensions in play, this D and P, and the cosmological constants you start with. Okay. Now let's do the same thing, starting with vacuum and same gravity. It's in n plus p plus 3 dimensions. It's just because it's convenient to choose these tiny dimensions, but the idea is here we want to reduce it over a manifold that has n plus 1 dimension in such a way that we end up again with an action on a manifold that has p plus 2 dimensions. Okay? But in this case, instead of reducing over a torus, we reduce over a sphere with n plus 1 dimensions, and this is the ansatz. This time the conformal factor with the dilaton is completely factored out. And if you perform this reduction, you obtain again the same exact action, but no, I think the problem is the you obtain the same kind of action, but now the alpha and beta, these coupling constants, will depend on the new dimensions in play, this n and p, and beta doesn't depend on the cosmological constant like here, but on the radius of this sphere that is inside your rich manifold here. Okay? Now the interesting thing is that if you take D, that now it's not a dimension anymore, from the point of view of the lower dimensional theory, it's just a parameter that parameterizes these couplings, and you exchange it with minus n, okay, which originally was the dimension of the sphere essentially, but now again it's just a parameter in this coupling here. And at the same time you exchange the cosmological constant with the curvature of your sphere, well, you see that these two actions are exactly the same. So this means that any solution of ADS gravity that, of course, satisfies this ansatz can be reduced down here. Then we can perform this map and uplift it back to a rich class solution. Okay. Any question? Okay, so this gives us a very simple recipe to map families of ADS solutions to families of rich class solutions, because you start with a family of solutions that is a solution for any dimension E, so it must be, the dimension must be free, a free parameter, okay, that satisfies this ansatz. You can extract a metric, that is this p plus 2 dimensional metric here, and the dilaton that defines the size of the torus here. And then once you have these two fields, you just perform this analytical continuation or simply substitution and obtain two new fields that when you plug into the ansatz that we had for vacuum and gravity, that is, you add a sphere, you take the direct product of this metric here in the sphere, and then you add this particular conformal factor, well then this metric here is automatically rich flat. Okay. So we have a very simple way to go from anti-de Sitter to rich flat, or vice versa, from solutions that are rich flat to solutions that are anti-de Sitter. Okay. Now, I should do some remarks. First of all, I already said it, but we need to know these solutions for any value of the dimension D or the dimension n of the sphere. Okay? So you cannot just take your favorite solution in 4 dimensions and try to map it somewhere. You must have a family of solutions that is valid for any number of dimensions. And moreover, this analytical continuation happens really on the lower dimensional theory, so these dimensions should really be thought of as parameters, okay, and not as dimensions. This is an example of generalized dimensional reduction that consists in doing such, you take a brain, you compactify on a torus, and then you analytically continue this dimension of this torus, and like this you can construct non-conformal brains and develop all the holographic dictionary. So the story is very similar, and hopefully it will allow us, in the same way as it was done here, to develop a holographic dictionary for acoustic spacetimes, asymptotically flat spacetimes. And then, well, there are also extensions where, for example, you can relate ABS to the sector, depending on what kind of geometry you are compacting. So, but definitely these rich flat solutions that you obtain, they have some underlying holographic structure that is inherited from the holographic structure of the asymptotically ABS spacetimes. Okay. So let's see some simple applications and see what happens to the simplest solutions we know under this map. And for example, the first thing we want to try to do is to take vacuum solutions. So for example, we can take ABS in d dimensions, d plus 1 dimensions, okay? This is in Poincare coordinates, and you see that here I have separated the boundary directions in some normal boundary directions, and then a bunch of them I can compactify them on a torus, and so I can perform the map over this torus, and what you obtain, well, you have to substitute, to plug it back in the ansatz as before, this conformal factor R squared over R squared becomes essentially the conformal factor we had in the ansatz before. And well, things conspire that when you use this map and you go to vacuum and gravity, you end up with a solution that is precisely in Minkowski in this particular coordinates, where the boundary metric that we had here, that remains here, the direction that were not compactified in the S, becomes some extended Cartesian directions in Minkowski, and the sphere that we are adding through the map combines with what was the holographic direction to give you some other flat directions. The interesting thing here is that you see that the boundary metric eta AB here ends up being in the center of ABS, in the sense that it's the metric that you have restricted on the submanifold R equal to 0. So it's like if it were a brain located in R equal to 0. So let's see if this interpretation holds. And so this will give us our first entry of the holographic dictionary. So on ABS, the boundary condition was to choose a metric at R equal to 0, so that's the conformal boundary. In this example, we chose just to take the Minkowski metric, and this translates on the rich flat side into a choice of a metric at the location of a figure. Okay. Now let's try to put excitations in ABS and see what happens on the Minkowski side. So let's take ABS in Poincare coordinates like before, but let's add a normalizable perturbation, that is, let's turn on a holographic, a dual stress tensor but only with legs on the directions orthogonal to the torus over which we want to compactify. Okay, we have frozen the torus, and in this way we can apply again the ADS rich flat map to get a solution that will be, well, like here you get the deformation of ADS, you will get some deformation of Minkowski spaceline. And it turns out that if you do this exercise, it's very easy. It's, yes?
Is there any relation between, so the dimension D that you originally had in the ADS spaceline, is that related at all to the number of P brane in your cross?
No, so what I'm doing here is, so ADS, I consider it in D plus 1 dimensions. So this D is really the number of boundary.
Sure, the size of the boundary,
yeah. And then I reduce to some manifold that has P plus 2 dimensions. Okay? So essentially, I reduce on a torus that has D minus P minus 1. So this is just the way we do, because in this way here, if you have our space-time that is rich flat, okay, then we have n plus p plus 3 dimensions, yeah, and we reduce over n a sphere that has n plus 1 dimensions, and again we get the lower dimensional theory that is in p plus 2 dimensions. The reason why we chose this number here is because that's quite standard in ADS, and on this side, in this way, the map is really simply taking d to the minus n.
So that's the P brane in the P plus 2 dimensional spacetime.
So
how large is memory possible?
it's p plus 1, p plus 1.
P plus 1. Okay. So you could have a 2 brane in a 3-dimensional spacetime, which is actually possibly flat. Well, because
Yeah, it's p plus 1, sorry. So p is really the number of station direction of the brane. It's really a p brane.
yeah.
So this is what you are asking. Yeah.
In P plus 1 dimensions or 2.
Well, once you uplift here, it's still a p brane, this one.
Yeah. Okay, sure.
Okay. Other questions? Okay, now if you do this exercise and you look at the perturbed Minkowski vacuum after doing the map, what you see is that you get some gravitational perturbation, HAB, that actually is the solution of the linearized field equations sourced by the stress tensor TAB that was essentially the one leading that we used to introduce the normalizable perturbation in ADS. Okay? So the dual stress tensor in ADS becomes really the stress tensor of this P brane. Okay? And really generates the faraway field, faraway gravitational field. So one can think, well, what happens to the two-point function that we obtained before? Remember, we asked for regularity in bulk and solved for the fluctuations, and we obtained this function here. Now, all we have to do to obtain the corresponding perturbation of Minkowski spacetime is to send d to minus n, and okay, one obtains this formula here, but if you analyze it, then you discover that this is, as I was saying, just a linearized gravitational field produced by a P brane with world volumetric eta u plus h nu, and also it falls off exponentially at infinity. So the metric remains asymptotically flat, at least in the directions orthogonal to the brane. And what you can see is really that this condition of regularity in the interior of ADS is the equivalent through this map to the requirement of asymptotic flatness in Einstein vacuum gravity. Okay? So this allows us to add two entries to our holographic dictionary. And so first of all, at linear order, the holographic stress tensor becomes the stress energy tensor of the speed brane, sourcing the linearized gravitational field. And in particular, the regularity in the interior of ADS is mapped to asymptotic flatness. Okay. So these are little hints that we are getting, but it seems, at least from this perspective, that if one wants to develop some kind of holography for asymptotically flat spacetime, one has to talk about branes living in the bulk of Minkowski, and not looking at putting asymptotic boundary condition on a spatial infinity, for example, of surface. Okay, let's continue. The next interesting thing is to try to thermalize these branes. And so you can start with planar ADS black holes. And again, it's not difficult at all. You can perform the map, and well, no surprise again, you just get a Schwarzschild brane, okay? Because essentially the Blackman form function here gets mapped into the one for Schwarzschild branes, and the field decays like 1 over r to the n, so this is really for a brane that has n plus 1 transverse directions, as you would expect. And then these directions that were staying in the boundary of, the direction that we didn't compactify along the ADS brane just becomes the extended directions of our asymptotically flat brane. Okay. And actually, this can be performed also on the ADS fluid gravity metric. That is when you take so in the hydrodynamic limits we have up to second order derivative expansion of the fluid solution to the perturbations of these planar branes. And the nice thing about these solutions is that, well, we know them for arbitrary dimension B, so this is again a case where we can perform our map. And if we do this, we really obtain what was called the Blackford, that is the effective theory describing long wavelength perturbations of Schwarzschild black branes. And one very nice thing that you can find very quickly is that if you look at the equation of state for this for the fluid describing the planar ADS black hole, well, this is completely fixed by conformal invariance. So essentially, you have that epsilon, the energy density, must be equal to d minus 1 times p. Okay? And so the speed of sound, the speed at which the perturbation propagates along the extended direction of these branes will be the p in the epsilon, the speed of sound squared, which is, well, the one moment result is 1 over d minus 1. And if you do this, the map directly on these things, you get the equation of state. You see, you have to send d to minus n, and you get the equation of state minus n plus 1 p, which is the equation of state that you will find in the effective theory describing the long-wavelength fluctuation of a Schwarzschild brain. And in particular, if now you compute the speed of sound squared of these perturbations here, you just send b to minus n, so you see that c squared is negative. Okay? So this means that any fluctuation of perturbation will not propagate, but will just grow, okay? And this signals an instability, and this is precisely the Gregory-Laflamme instability of black brains or black strings, right? If you have a black string and you perturb it with a wavelength that is larger than the transverse size of your horizon, then you have this perturbation will grow exponentially and disrupt your horizon. Okay? So actually, with this map, we were able to take all the fluid gravity metric up to second order derivatives and map it to Minkowski, and we recovered. We got an extremely good agreement with numerical results, at least for a large number of dimensions, with more dimensional Bernoulli agreements in a totally analytic. So this is another example where you get interesting results. Now the problem, so essentially this ADS rich flat correspondence maps asymptotically locally ADS solutions to rich flat spacetimes, and these rich flat spacetimes, as I already said, they inherit the holographic properties of ADS. That's why we're so interested in this correspondence. The problem is, well, it works well for all the directions transverse to the torus of the sphere, so all the extended directions of your brains, for example. However, this manifold, this torus and this sphere over which you are compactifying, you have to freeze them completely. And if you want really to understand choreography for asymptotically flat spacetimes, you really have to understand also what happens with modes that deform this internal sphere or torus, because, well, for example, in the case of the Schwarzschild black hole, you would, if you're freezing completely the sphere that is there, you're freezing all the modes, okay? And so you're killing all the dynamics. So we have, what we want to see now is how much we can really push this correspondence and extend it to the most general space. Any question? Okay, so let's try to unfreeze torus and spheres. So this, I will start talking about the most recent results. And, well, the idea here is, if it can work, well, it has to work also at a linearized level. So let's first work with linearized perturbations. This, as we saw it before, it will be already enough to understand, for example, correlators of two-point functions. So as a first step, it's an interesting one, and it will tell us whether the map can be extended. And the idea is to allow for arbitrary perturbations, arbitrary fluctuation on the torus and the sphere, perform full Kaluza-Klein reductions down to the p plus 2 dimensions, and then compare the resulting modes. Okay. So I will not enter in many details, but the idea here is that this is the ansatz for Minkowski in n plus p plus 3 dimensions. Like I showed you, that's what we obtain from the ES, right? Here is the sphere, and then we take a perturbation of Minkowski, but this perturbation, we allow it to have legs and depend also on the coordinates of this Sn plus 1 sphere. So the idea is that you expand all the fields in harmonics of the n plus 1 sphere, and you get a number of scalar vector and tensor fields that live on this space-time. Okay? And you can do the same thing in ADS. It's a bit easier because now we are dealing with Fourier modes, not necessarily harmonics, but you obtain a similar bunch of fields. And then you have to perform the full horizontal reduction. This takes some time. It's not particularly difficult, but it's a long computation. And the systematic way to do it is to construct gauging band combinations of all these fields, and then you can linearize the full Einstein equations for these perturbations and rewrite them in terms of missing bands. Okay? And while you obtain a number of field equations, and actually here they're not meant to be read, but these are the invariant actions, the quadratic actions for the fluctuations for all the modes on the torus and the sphere. Okay? And this is an interesting result in itself because apparently we didn't find it in the literature, so it might be useful. Anyways, once we have all these equations, the other interesting thing is that we can completely decouple them and solve them. Okay? So let's see what we obtain and whether we can somehow match these modes. So the first thing one can look is at the limit of large dimensions. Okay? And well, it turns out that all the solutions, both in ADS and in Minkowski for these modes, are by some polarization tensor of vectors times r to some power, and then some Bessel function with index. Okay? And in the extended direction, we have just Fourier modes. Then, in the case of vacuum gravity, you also have three terms in these Bessel functions. In ADS, they are not here. And the values of these coefficients, A and B, are given in this table. And of course, they're different. But the interesting thing is that in the limit where n or d is large, where these red terms are the ones that dominate, you can just neglect the constant factors. And then if you send n to minus d, you get the leading terms in ADS. So in this large n or d limit, we see that there is complete agreement between the linearized modes on ADS and Minkowski, even when you relax this assumption that you are freezing the internal factors. Okay? This is not really surprising. Essentially, gravity becomes very weak, and in these limits, and the curvature of the sphere or the effect of the technological constant essentially become negligible. And that's the reason why we call this here.
Sorry, Mike.
Yeah.
Why the coefficients don't quite understand how you mark them?
So this is in Minkowski in n plus p plus 3 dimensions. Okay, and the map, to map it to ADS, you must take n and just substitute it with minus d. And if you do this, well, I should have put this sign in red also. Here, for example, you have minus n half, and if you send n to minus d, this becomes plus d halves, which is exactly the
Yeah, this works for the A, but it doesn't work for the B.
oh, you're perfectly right, but actually these are half integers, indices of these set functions. So actually, you can change the sign of the set functions. Good. Any other question? Sorry, how much?
30 minutes.
15 minutes, okay. So, okay, this is in the large n and d limits. What can we do for finite n or d? Well, it seems desperate, right? Because on one side we have modes that are in terms of harmonics of the sphere, and on the other side we have Fourier modes. So the spectra cannot match. Okay? The eigenvalues of the Laplacian on the sphere and the torus are just different. So it seems difficult to find out how to reconcile them. And but actually the idea is that, well, we don't need to preserve the full sphere or the full torus. If you take a perturbation that just deforms a finite number of directions in the torus of the sphere, but there still remains an arbitrary dimension sphere or torus over which we can do the math. Okay? Let me be more precise. So let's consider, for example, a mode of Minkowski that depends on the sphere. So we take this perturbation to preserve some SOn plus 2 invariance of the full invariance of this sphere here. And now, well, since this was a solution for arbitrary values of n, and if we fix, well, this number n, big N, will still be allowed to assume any value. Okay, so we can just perform the map over this subsphere. Okay? And so we perform the ADS-Flat correspondence on Minkowski, but on this subsphere. And now, well, we obtain some ADS perturbation that, when rewritten in terms of, you change coordinate to reconstruct the original torus that you have here, and now you will have some dependence on the coordinates of this torus. But the main point is that the single Minkowski mode here doesn't give you a single ADS mode under the map, but it will give you an infinite superposition of these modes. Maybe a diagram will help to clarify what we are doing here. Essentially, it's very simple. We are just taking this Sn plus 1 and write it as a fibration over a segment of two spheres, okay? And we continue to freeze this bigger one with S big N plus 1 dimensions, while we allow this one that has a fixed number of dimensions, we take small n minus big N to be a constant, we allow perturbations over it. And this you can map it, and it gives you infinite superpositions of modes over the torus of yes. And you can do exactly the same thing, start from ADS and go into Minkowski, and you will just obtain some infinite superposition of modes on Minkowski that depend on your n plus 1 sphere. It's interesting actually that you can perform this map also on some nonlinear solutions, so some plane wave solutions that are solution both of the linearized and the full Einstein equation, and this works. So this is an indication that is now, we still don't have the most general thing, right? Because we are still freezing part of the sphere here. However, now what we can do as a final step is to take this big N and send it to -1, for example, and just eliminate this code. Okay? So essentially, we collapse this extra sphere, and what we remain with is simply the most general perturbation of some of Minkowski or of ES on the other side. So this works as follows. Essentially, if you have a map between some ADS gravity solution, family of solution with with this torus and the rich flat solutions with this sphere, well, you can show that this limit in which you collapse this sphere is regular, and you will get some rich flat solution in a finite number of dimensions. Okay? So let's suppose you are interested in the physics of this rich flat manifold. The idea is you find a way to uplift it up to this arbitrary dimensional rich flat manifold that can be mapped to some ADS gravity solution. Here we can rid of things using holography or stuff, and then on this physical quantity that we compute on the ADS side, we can perform again this n goes to -1 limit and obtain the physical quantities for this rich flat. Okay. The only problem in all this is that if you give me an arbitrary 4-dimensional solution, rich flat manifold, it's a very hard problem to show that you can actually uplift to, that can be obtained as a limit of some rich flat manifold that has an internal Sn+1 sphere. Okay? So, but however, you can. It's a well-posed problem, and at least perturbatively, we were able to show that it is possible to solve it perturbatively in this dimension. And you can do the same thing on this for if you are interested to rid of from ADS rich flat solutions some physics for ADS. Is it clear or? Okay. So this is the idea, and well, actually, one specific example of this we worked it out in full detail in one of the old papers, and this is the limit where you take a p-brane and take this n goes to -1 limit. This metric becomes Ringler spacetime, and if you take the fluid gravity metric in ADS, okay, which is known for any value of the dimension, you map it, as I showed you before, to the long wavelength perturbation of the black p-brane in Minkowski, and then take this limit n goes to -1, you obtain Ringler, the Ringler fluid metric to second order, because you start with the second order, and you recover all the correct transport coefficients. So this is an example where you can work this out in full detail. It's very complicated because there are divergences and so on, but it's possible to cure them, eliminate them, and find a finite result that is correct. Okay, so these are the conclusions. So we have seen, oh, even the projector is tired. The perturbation of Minkowski spacetime can be mapped to perturbation of EBS spacetimes. We were able to unfreeze completely the sphere and the torus that are in the original version of the EBS which reflects correspondence. And in particular, we checked that in large dimension limits, individual modes are mapped into each other, so it's really very clean there, the correspondence. And at finite d or n's, the single modes are mapped to superposition of other modes. Okay. And asymptotically flat spacetimes inherit the holographic properties of ADS. And what I showed you is some very rough holographic dictionary that we are developing, and in particular what we discovered is that the data are encoded in a different way than what people were looking for when looking for asymptotically flat holography. In particular, the source of the dual operators are located at the position of a p-brane, and the stretch tensor due to this p-brane is holographic. And finally, the asymptotic flatness is the condition that is the analog of the regularity condition that you get in the S1. Now, there is really a lot to do. It's still in its very early stages, this project. So feel free to try to use these things, because I think it's very promising, and maybe with some different approach, more geometric approach, you will be able to find things that we didn't think about. But what we are really interested in would be to apply these methods to Schwarzschild black holes, and use this generalized conformal structure that are visible in rich spacetimes to find all the predictions. And finally, this map is a solution generated technique at the end of the day, so it might give us surprises. So thank you very much. This is the takeaway message. It's not to be taken literally, but almost.
Questions or Marco?
I have one. You said there is a generating technique, so basically you can generate new solutions with this technique. And have you ever seen that if you take a black hole in the ADS space, you can find another type of black hole never found on Minkowski asymptotically?
Yes, but the fact is that if you start with a planar ADS brane, what you obtain are the Schwarzschild branes that were already known. However, the metric that perturbed to second order in derivatives with long wavelength perturbations, this we mapped it to Schwarzschild, and the solution there was not known. It was maybe not the fastest way to get to that. Maybe working it out directly, I'm not sure. But maybe in other cases, the problem is that you need to have these thoughts there, so you can't just start with a black hole in global.
Yeah, I'm thinking like those supersymmetric ADS5 asymptotically black holes. Well, I don't know. Also, if you add a supersymmetry, what happens to this duality?
So the other problem here is that it's not very flexible, and we didn't find any simple way to add matter, and in particular fermions would be very difficult to add, because you see, you need a solution that is a solution for any value of the dimension, because you will not have fermions in any dimension. So it's not clear at all to me that these things can be extended to some supergravity setting. But on the other hand, it allows us to understand really the common sector that is in any of these ADS CFT viewers. And once we understand this part, maybe it will also give us some hints of how to extend these things.
So maybe you have a kind of hint if it's generalizable to Einstein-Maxwell dilaton theory.
Well, if it's an Einstein-Maxwell dilaton, the couplings that come from by dimensionally reducing from a vacuum Einstein gravity, yes.
Okay, that's great.
But that's the only kind of matter we know how to do.
Yeah. That's why I asked. No, I didn't know.
Okay, more questions?
If you were to allow for the asymptotic symmetries in EMS calculation, do you have any insight of what it would do?
So the boundary, well, no, not really. The boundary of Minkowski should be mapped. So if you just look at Minkowski, so without entering it, this boundary would get on the Poincaré horizon. So you should find this kind of generators on the Poincaré horizon in ADS. And the reason is, I think, that you should be able to find this kind of symmetries is that it's an extreme horizon, which is exactly the same kind of singularity that you have at asymptotic infinity. In the sense, so it's been a while that but yeah, I'm sure there must be some interesting things to do. It's just we didn't get there. So definitely, one can take the symmetric and try to. It would be interesting.
More questions?
Maybe you said that, but is it possible to take that further to the zeta space?
Oh yes,
What's that is? Could you
yes. It's actually.
Okay, so maybe.
So here you see this cosmological constant ends up is swapped with the radius here. But if you just take twice the dimensional reduction of this, and here, for example, you reduce on a sphere, and another copy, but with I mean, you can play with the internal manifold, you can take hyperboloids and spheres, and this gives you different values for this beta here, and so you could exchange, you can manage to exchange the negative cosmological constant of ADS into a sphere, I think, or which you compactify in the sector, and the positive cosmological constant of the sector, it will become the curvature of a hyperboloid on which you are compactifying ADS. So by choosing your reduction, your compact manifold over which you reduce, and the signs of the cosmological constant, you can get values, and in particular also the sector sort is very similar.
If there are no more questions, thank you.